S. Chand presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
You might have heard about Newton's laws of motion, but what is the real life applications of those Newton's laws in engineering? In today's class, we will be learning this concept. Welcome to S. Chand Academy, and I am Anmol Bhatia. In today's class, we will be learning about Newton's laws of motion and its relevance in engineering. For detailed conceptual clarity, you can refer to this book by S. Chand Publishing. The link of the book is there in the description box below. So this is the course on engineering mechanics, and we are doing module number 1 of the course, and the topic that we are covering in this lecture is Newton's laws and its completeness in describing the particle motion. There are 3 laws which are related to motion, and these laws were given by Newton, starting with Newton's first law. So Newton's first law basically states that if a body is at rest, will continue to remain at rest, and if a body is in motion, it will continue to remain in motion unless and until an external force is applied on it. This is the basic statement of the Newton's first law of motion. Here what happens, let us say we consider 2 bodies, which is the first body which is at rest and the second body which is at motion. So the body which is at rest will remain at rest, and the body which is in motion will continue to remain in motion unless and until we apply some external force on the bodies to move this object and to stop this object. Here you can see that the velocity is constant, and the constant velocity here is termed as a uniform motion. So the term uniform motion is there in the definition of Newton's first law. So Newton's first law is basically related to those kind of activities in which the particle is there in motion. And the term which is basically associated with Newton's first law of motion is inertia. So inertia is basically that property of the body due to which it basically resists the change in state of rest or of uniform motion. Let us say, for an example, if you are beating a carpet. So if you beat a carpet, then dust particles may come out of the particles. Why is it so? Because the particles were initially at rest and the carpet was also at rest, but if we start beating that carpet, so what happens, the carpet will come to motion, but the particles are still at rest. So due to inertia property, the particles would fall down, and we notice that the particles coming out of the carpet. So this is basically related to Newton's first law of motion. Then Newton's second law of motion, and what the statement says about the Newton's second law of motion. So Newton's second law of motion is basically indicative of the statement, and it states that the force applied on a body is directly proportional to the rate of change of linear momentum of the body. So here there are 2 terms, one is this force term and another is this momentum term. So let us understand what is momentum, and then we come to this law mathematically. So momentum is basically a term which is related to mass and velocity. So momentum is a kind of property of a body which is related to mass and velocity. Let us say there is a body which is having a mass m and it is moving with a velocity v. So momentum is denoted by this term which is p. So here, as you can see, that the formula is momentum is equal to mass and velocity, the product of mass and velocity. So momentum is basically described as a physical quantity which is indicative of the product of mass and velocity. So the law states that the force is directly proportional to the rate of change of linear momentum, and what is it? So the force value, the force which is applied on a body, that force is directly proportional to the rate of change of momentum. So rate of change of momentum is basically the derivative of momentum. So if we differentiate this value of momentum, we will get the force. So if this force is F and we keep directly proportional as it is, so derivative with respect to time of momentum is mv. So the formula for momentum is mv, and as you can see that the mass is constant for an object. So considering mass as constant, F would be directly proportional to mass comes out of this derivative function. So this becomes dv by dt. So the derivative of velocity is acceleration. So force is directly proportional to mass multiplied by the acceleration value. Now in order to remove this directly proportional term, I will have this equal to term and F equals to k multiplied by mass into acceleration. So for the sake of removal of the constant, we keep this constant value as 1. So the formula becomes mass multiplied by acceleration. So this formula, or from this formula we can also define the force part. So mass multiplied by acceleration is basically the force. So the relationship amongst force and momentum, or the force and the rate of change of momentum, is being defined in the second law of motion. So let us understand it again. The force part is directly proportional to the rate of change of momentum. Momentum has this formula, so I substitute this formula here and then I will derivate it with respect to the time frame. Mass is constant, so I can take this mass as outside of the bracket and then I will derivate it. So the derivative of this velocity is acceleration, and then I solve this, so that force comes out. So this is what we derived in the class. So F is directly proportional to the rate of change of momentum. So we substitute this value of momentum as mv and keeping this mass as constant. So the final value that comes out is F equals to mass multiplied by the acceleration. So mass multiplied by the derivative of this velocity. So derivative of this velocity is acceleration. So F is directly proportional to mass into acceleration. We substitute or remove this is directly proportional sign by equals to and put k. So F equals to kma and put k as 1. So ultimately we will get the value of force as mass multiplied by acceleration. So force is basically what? Force is a push or a pull which is exerted on a body, but that push or a pull is responsible for creating certain changes in the body. Likewise, the force can change the shape of the body, the force can change the motion of a stationary body or a moving body. A force can also change the shape of the body, size of the body and whatnot. So the thing is the force part and momentum part. So a basic relationship between force and momentum is being given by the second law of motion. Now before coming to the third law of motion, there are several cases which are associated with the third law of motion, and wherein comes the engineering concepts, like when we want to create certain structures or when we want to apply forces on different objects, then these kind of laws comes into picture. Like for an example, if I tell you that I need to create a bridge on which the vehicles would be moving. So that bridge would be a kind of situation in which there is a particle which is there on the surface of that particular bridge, and there must be some forces which are acting on the surface, and in order to sustain or in order to calculate what would be the life of that particular bridge, these laws are applicable. So we stop here for a short break. After coming back from the break, we will learn about the third law of motion and the basic applications of the third law of motion and how it is related to engineering aspects.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy. Before going to the break, we have learnt about Newton's first law of motion and Newton's second law of motion. We have also derived the mathematical expression related to Newton's second law of motion. Now, in this video, we will be learning about Newton's third law of motion, and we will discuss certain applications of Newton's third law of motion in context to the engineering perspective. So, Newton's second law of motion is basically the type of law which basically defines a mathematical relationship between force and rate of change of momentum. So, as I have told you that this force is the force which is applied on the body is directly proportional to the rate of change of momentum, and we have derived the expression in the video before going to the break. So, that expression was F is directly proportional to dP by dt, and when we substitute this P, which is momentum, into the expression, we will get mv upon dt. So, mass is constant in the first case. So, I have taken this mass as common and I have derivated this velocity with respect to time. So, the derivative of velocity with respect to time is acceleration. So, I will substitute this k in place of this direct proportion, and if k is 1, I will get this value of force, which is ma. But there is a twist in this particular equation. Now, what is the twist? Till now you have learnt about the constant mass concept. Now, what is the case when the mass is not constant? So, in the real life application, you will come across the situations in which the mass is not constant. Like if you are dealing with the flow of any fluids. So, in case of any fluid flow, that fluid also exerts a force on the surface. So, in that situation, we cannot take the mass as constant. So, when mass is not constant, the same second law is again applicable, and for that F is directly proportional to the rate of change of momentum, and if I put this momentum value into this expression, I will get mv. Now, if this mass is not constant, then I cannot take this mass as common, or I cannot take out this mass from the derivative equation. So, what I need to do? I need to derivate it with respect to time and keeping this as a single entity. So, I need to derivate using a product rule. So, mass, this first function remains as constant, and the derivative of the second function plus the second function and the derivative of the first function. Now, this is an expression when the mass is not constant, and derivative of this velocity will be indicative of acceleration. So, you will get you will remove this direct proportion sign and you will get the value of this direct proportion as k by writing equals to against this expression, and you will substitute k as 1. So, this expression would be the expression when the mass is not constant. In case of this part, in case of this dV by dt, you can substitute it as acceleration, but this term will be there in the expression. Now, following this expression, if mass is constant, so if the mass is constant, this term will become 0 if the mass is constant. So, the derivative part will become 0 for the constant. So, this becomes 0, then again you will get the expression as F equals to ma. But if this mass is not constant, or you can say if that velocity is constant, let us say the water is moving with the constant velocity. So, this term will become 0. So, if this term becomes 0, then V dm by dt, where dm by dt is the rate of flow of the mass. So, mass flow rate is this term, which is dm by dt. So, F again will be equal to F equals to V times dm by dt. This can also be the expression for Newton's second law of motion. So it depends upon the situation, what is the condition given for the mass value. If mass is constant, then you can directly consider this mass outside the expression or outside the derivative part and just derivate it with respect to the single term. Otherwise, you can use the product rule for opening the equation up and then consider the cases. Now, the Newton's third law of motion. So, Newton's third law of motion basically states that if there is an action, there would be an equal and opposite reaction, but that equal and opposite reaction will be on the other body. So, if we look at the statement says that to every action there is an equal and opposite reaction, but acting on different bodies. So, we cannot say that if a body is experiencing an action, then the same body will experience a reaction. So, the reaction would be on the other body. So, this part would be applicable to two different bodies. So, this is basically the statement which is behind Newton's third law of motion. Now, let us look at certain engineering applications or engineering perspectives of this Newton's third law of motion. So, as I have told you that to every action there is an equal and opposite reaction, but that is acting on different bodies. Let us say I have a wall and let us say a beam is there on the wall and I apply the force on the beam. Let us say I apply the force on this direction on the beam. So, what happens if I talk about the engineering perspectives, I need to break those components into certain components, and those components are called as the free body diagram. I need to free all the components from the forces and make a free body diagram in order to understand that which component is the action part and which component is the reaction part. So, initially this is having a force, this wall is again having a force. So, this wall will be having an action and this wall will have an opposite reaction on the surface. If this object is having an action, so this object is having the action part again, which is called as PA, but the opposite, which is the wall, will have a reaction, which is this. If this is having an action, then the wall would have a reaction. So, if this is having an action, this would have a reaction component. And if let us say a man is standing over here and this man would experience a reaction from the surface. So, if this is an action, then the man would experience a reaction. So, this would be the segmenting or segregation of all the components so that the analysis of the forces would take place. And in case of engineering perspective, the analysis of forces is important so as to have the initial or the overall deformation in case of the component which is undergoing certain set of forces. Let us consider another set of example. Let us say I have two masses, the first mass is m1 and the second mass is m2, and I am applying a force on the surface of the two masses. So, what happens, this m1 mass will experience an action, and I have told you that it is for the different bodies, the reaction is for the different body. So, this m2 will experience a reaction force. So, this is the free body diagram which is made in accordance with the third law of motion. So, this free body diagram is very helpful in terms of performing these engineering calculations. Then there is a description about the two categories of forces. The first category of the force is the normal force. So, the normal force you would come across many a times in the numerical section, that there is a normal force, there is a tangential force. So, what basically is the normal force and what is the tangential force? Let us understand that. Let us say I have a block and that block is having a mass, and that mass is m, the mass of the block is m, and let us say the block is having, or the block is placed on the surface. So, the block is placed on the surface and the block is exerting the force which is mass multiplied by the acceleration due to gravity, which is mg. So, the weight of the block is exerted downwards on the surface. the opposite reaction will be experienced from the surface on the surface of this block, and that would be the normal force. So, the normal force would be this opposite reaction and the action will be mg. So, mg and np are the two action and reaction forces which are there. So, normal is basically the perpendicular force on the surface. Let us say I have a block like this and a force which is acting perpendicularly on the surface, perpendicularly acting on the sheet of paper. That particular force is called as a normal force, as the name suggests. So, normal force is the force which is acting perpendicularly on the surface of the body. Then let us consider another case of this tangential force. So, tangential force is basically the force which is there on, let us say, some examples like string or ropes. Let us say I have a surface, and from that surface a 2 kg mass is tied, and this would experience a force which is equal to the weight of this object. So, the weight is mass multiplied by the acceleration due to gravity. So, mass is 2, so I substitute 2 here, and acceleration due to gravity is generally taken as 10. So, this W value is 20 Newton, and the similar 20 Newton will be experienced by this opposite force. So, this block will experience an action or will exert an action because of this weight, and the opposite reaction will be experienced by the string, and that will be this T, and this is denoted by this direction because of the equal and opposite directions. So, T here is basically 20, that is indicative of the tangential force, and this is generally applicable to the strings and ropes. So, third law of motion is basically that law that defines a relationship between action and reaction, and the important point to note is that this is applicable for different objects, not for the similar objects. And we have discussed certain applications which are related to the forces, how these forces are responsible to create the reaction. So, we come to the end of the lecture. In this video we have learnt about the third law of motion, and also we have learnt about the details of the second law of motion. For detailed conceptual clarity, you can refer to this book by S. Chand Publishing. The link of the book is there in the description box below. If you find the video interesting, like, share, subscribe the channel and hit the bell icon for future updates. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.